continuing a review of pre-calculus, this notion of functions and relations. We'll start out with relations. A relation is a set of ordered pairs. It could be expressed by either listing the ordered pairs or with a formula. More typically, in Calculus 1, we'll be expressing functions with a formula, but it could be a list. So here's some examples of relations. The relation A is a set of three ordered pairs, 1, 4, -1, 4, and 2, 5. The relation B is an infinite set of ordered pairs. It's a set of all ordered pairs x, y with the real coordinates such that x squared plus y squared is equal to 25. And you may recognize this equation from pre-calculus. This is actually a circle with radius 5 and centered at the origin. We can pick some values of x and y that fit the equation that will help us make the graph. If x is 0, y could be either 5 or -5. If x is plus or minus 3, 3 squared is 9. Then y would be plus or minus 4. 4 squared is 16. 9 plus 16 is 25, and so forth. So we can write pairs of points that fit the equation and then connect the dots, and the graph is a circle. So that's those are two examples of relations. The domain of a relation is the set of first coordinates. The range is the set of second coordinates. So for relation B, we can see from the graph that the domain and range are both go from -5 to 5. The x values go from -5 to 5, and also the y values go from -5 to 5. We can also, even without the graph, if you look at the formula, x squared and y squared cannot be negative. So that means that x squared is at most 25, because if you add 25 to something positive, you're going to get something more than 25. So x squared has to be at most 25. That means x itself has to be between 5 and -5. And then you could say the same for y squared. Y squared can be at most 25, and that means that y itself has to be between -5 and 5. Okay, so here's some more examples. If I can get this out here. Find the domain and range, and we're going to be assuming, for the most part, we'll be assuming that x and y are real numbers. If you allow imaginary numbers, x squared could be more than 5 if y could be imaginary, and likewise y squared could be more than 5 or y could be more than 5 if x is imaginary. So, but we're mostly going to be working with real numbers. The domain for this relation, this was relation A, the set of first coordinates. So the domain is going to be the set of 1 and 2. The first coordinates are actually 1, -1, and 2. I left off 1, -1, and 2. And the range is set of 4 and 5. There's the second coordinates are either 4 or 5. Example B, actually, the domain, the range is a little bit harder. If we solve this for x, we can get the range, but the domain is easy enough here without going to too much trouble. For a fraction, for real numbers, you can multiply any real number by 2, and you'll get a real number. You can divide by any real number except for 0 and get a real number, but you can't divide by 0. So the only restriction on the domain here is that x cannot be 3, because if x is 3, you're going to have denominator 0. So the domain is set of real numbers x such that x is not equal to 3. And you could write that in interval notation. It's minus infinity to 3 with an open parentheses at 3 to indicate that 3 is not included, and then union 3 to infinity. So that's the answer in interval notation. This is the answer in set builder notation. The other thing to look for, the two main things to look for when you're restricting domains, actually there's three things to look for. One is denominators. You can't have denominator 0. And the other is an even root. We'll mostly be working with square roots, but any even root, the expression under the root cannot be negative unless we're working with imaginary numbers. So 4 minus x squared has to be greater than or equal to 0. If you add x squared to both sides, that means that 4 has to be greater than or equal to x squared. And so that means that x squared has to be between 2 and negative 2. So we can usually write the letter on the left. So we can write this x squared as less than or equal to 4. And if you think about what numbers squared will give you, will be less than or equal to 4. Maybe sometimes it helps to make a picture. No, 3 is too big. 3 squared is 9. That's too big. Negative 3 squared, you want to square the minus sign, so that's going to be too big. So it's going to be the numbers between negative 2 and 2. So so x, so the domain is going to be the set of x such that minus 2 less than or equal to x less than or equal to 2, or an interval notation. You could write square brackets, minus 2 comma 2. The square brackets indicate that you include negative 2 and 2, and that you include the 2 endpoints. Okay, some more examples. There's no restriction on the domain for function d. I mean relation d. There's you can negative 2 times any real number is going to be a real number. 3 added to any real number is a real number. Absolute value of a real number is a real number. So so there's the domain is sometimes expressed as with the script R to indicate all real numbers, or in interval notation it would be round brackets minus infinity to infinity. And this one is also domain is all real numbers again. You have to be a little bit careful about denominators. Denominator can't be 0, but as long as we're working with a real number system, any number squared is going to be either positive or 0, and if you add 1 to it, you're going to get something positive. So this denominator, x squared plus 1, cannot be 0 unless we're working with imaginary numbers. So the domain is a script R, all real numbers, or an interval notation. It would be minus infinity to infinity. Okay. Another example. This is a denominator and a square root. So denominator cannot be 0. So this expression on the bottom cannot be 0. It also can't be negative because it's under a square root. So x squared minus 6x plus 5 has to be strictly greater than 0. We can factor this into the quantity x minus 5 the quantity x minus 1. You can check with the FOIL method. X times x is x squared. The outer product is negative 1x. Oops, it looks like I'm frozen here. Okay, now I'm unfrozen. X times x is x squared. The outer product is negative 1x. Inner product is negative 5x. Add those, you get negative 6x. Last times last, negative 5 times negative 1 is a positive 5. And so let's use a number line again. This expression is going to equal 0 if x is either 1 or 5. Then we can do some test points. If x is less than 1, for example, 0 minus 5 is negative, 0 minus 1 is negative, negative times negative is positive. Do a test point in between 1 and 3. 3 minus 5 is negative, 3 minus 1 is positive, negative times positive is negative. Do a test point bigger than 5, 6 minus 5 is positive, 6 minus 1 is positive. Positive times positive is positive. So the domain was going to be where it's going to be positive instead of x, such that x is less than 1 or x is greater than 5. And you can express that in interval notation. From the interval from minus infinity to 1 with round brackets, union interval from 5 to infinity with round brackets because we're not including the endpoints. Okay, now let's get into functions. Functions are very important in calculus because there's certain procedures that can only be done on functions. A function is a special relation in which each first coordinate appears only once. So let's look again at this the original example that we're looking at, the circle. This is not a function because, for example, if x is 0, y could be either 5 or negative 5, and you can see that on the graph. When x is 0, x could be 5 or negative 5. When x is 3, y could be either 4 or negative 4. You can see that on the graph too. So so each first coordinate appears more than once, and so here y is not a function of x. And what there's something there's a test called the vertical line test that you can use on a graph. There's certain places on this graph where if you draw a vertical line, the vertical line is going to cross in more than one spot. So that's called the vertical line test. So if this function or this relation fails the vertical line test because there's certain places where you draw a vertical line, it touches in more than one spot. Another way of doing that is to solve for y. If we solve for y and we get more than one answer, then that means it's not a function. So if we start with x squared plus y squared equals 25, subtract x squared from both sides because we want to isolate the y. That'll give us y squared equals 25 minus x squared. And then take the square root. Well, most numbers have 2 square roots. So let's create the square root of both sides. And we're going to have to put plus or minus here because most numbers have 2 square roots. And the square root symbol only means the positive square root. So we want plus or minus square root of 25 minus x squared. So we actually have 2 different formulas for y. So y is equal to square root of 25 minus x squared, or y equals negative square root of 25 minus x squared. So this is the upper semicircle, and this is the lower semicircle. Okay. Okay, so we have two different formulas for y, so the original relation was not a function, and what we've actually done here is split this into two functions. And that's one of the strategies you can use in calculus if you're trying to do a procedure that can only be done on functions. You can split it into two pieces and do the procedure separately on those pieces. So we have the upper semicircle here. It's the upper semicircle, and this is the lower semicircle down at the bottom. Okay. So we could. So that's one way of handling it. But in any case, the original formula was not a function. Okay, so which of these relations represents functions? We have one that's defined by a set of ordered pairs, 1, 4, negative 1, 4, 2, 5. The other ones are defined by equation. And the answer is they're all functions. In part A, each x-coordinate appears only once, so that means it's a function. And the other ones, we all have y by itself. So you have y equals, that means there's only one formula for y. You have y by itself equals some expression involving x. So those are all functions. And that concludes this presentation.